Welcome, everyone. My name is Linda Nazar, and I'm delighted to welcome and introduce Professor Jürgen Janek, an old friend, an old collaborator, and outstanding scientist. Many of you probably know his work already. So Professor Janek is at the Physical Chemistry Institute at the Justus Liebig University, I pronounced that properly, in Giessen, Germany. And Jürgen has been collaborating, as I said, with us for, I think, some time. And today he's going to be talking about interface design. I can't read the title, so I'll just hammer this over around here. So Professor Janek has received many awards, too lengthy to enumerate here. One of them was the very prestigious Heinrich Hertz Award in 2025. Professor Janek is a member of the National Academy of Science in Germany, or the National Academy in Germany. And he also received their Greve Award in 2023, which is their highest honor. And is, of course, a member of the Academy. And Professor Janek is also an adjunct visiting or an adjunct professor at the University of Tohoku in Japan. And if any of you came to Professor Ono's talk, I guess a few weeks ago, that's what Professor Ono is the president of. So without further ado, having overcome our technical difficulties, thank you for all coming in the snow, and we welcome Professor Janek.
Yeah. Yeah, thank you, Linda, for inviting me. I think I gave a presentation, I would say somehow in the same setting, to August 2018, so 7 years ago. I checked my old slides to see that things have changed. So I think something has been improved, I would say, with content. And in fact, I'm quite happy to be here to continue our collaboration. And during my presentation, you will see a few results also from the cooperation. I see also quite some members from Linda's group. Lipin is here, who also spent some time in our lab. So of course, you're all invited. Once by chance you arrive in Germany at Frankfurt Airport, our lab is only 40 minutes door to door from the airport. So in fact, just referring to, if you ask yourself, okay, what is seen on this introductory slide, this is Justus Liebig, who is principal giving the university its name. He is one of the founders of modern chemistry, but he considered as one of the founding fathers of organic biochemistry and agricultural chemistry and analytical chemistry. And if you watch at this little tool here, which is the so-called 5-ball apparatus, you will see it on any ACS journal, any ACS product, you will see that in the logo of the ACS. And any member of the Liebig lab between 1820 and 1850 in Giessen had this at his jacket, because that was invented by Liebig. So, and is considered to be, I would say, today also an integral part, of course, of our history at JLU in Giessen. So if you publish at ACS and if you see the logo, think of my university. It's in the logo of the ACS. So as Linda said, I'm going to speak about solid state batteries. I will give an introduction into the subject, and I will primarily discuss interfaces. But of course, honestly, I'm a physical chemist, and chemistry means changing things. And so I'm interested in kinetics of cells, because if a cell has only energy, that's fine, but you have to get it in and out. So kinetic is very important. So I would say my true subject is identifying kinetic bottlenecks in solid state batteries and overcoming them, and finding ways to overcoming them. Before that, I'm sure not everybody of you is, would say, deep into the subject. So let me start by moving going briefly into lithium-ion batteries as a kind of benchmark. So you know, lithium-ion battery today is really a technology I think we really definitely need. There was a 2019 a Nobel Prize for lithium-ion batteries, which means that's definitely considered as being something that is valuable for human mankind. And what you see here is a cartoon of a lithium-ion battery, where there is, of course, the negative electrode and the positive electrode and the separator. The blue background is a liquid electrolyte, and the liquid electrolyte, in a sense, is really, I would say, enabling the lithium transfer between the electrodes, and it's really a great thing. It's wetting everything, it's connecting, it's really allowing ion transfer between these. Let's say there's typically oxide material storing lithium, here's graphite typically storing lithium, and the liquid electrolyte really is great. It's not ultra stable, and this is also one of the, would say, issues of modern lithium-ion batteries, that the materials here react with the liquid electrolyte, and has long been considered as one of the potential advantages of solid-state batteries, going ceramic, going to stones, to make ultimately stable batteries. I think you will see during my presentation that this is a wish, a hope, but in fact quite a difficult issue, as the best ion-conducting solid electrolytes are not that stable as one could think. They even may have a more narrow stability range than liquid electrolytes. They have advantages, but also they have disadvantages. So this is a typical Ragone chart, which shows in principle the possible power density as a measure of kinetics versus the specific energy, a measure of how much energy can be stored per mass. And I magnified this here, so this is from a nice paper of Yuri Gogotsi. You see here now in specific energy, so energy stored per kilogram of battery mass and cell level, including housing, but not a pack. So really the elementary unit, I would say, of a battery is the cell with its housing, typical cylindrical cells or stacked cells, pouch cells. And you see the green area here is what is today occupied by the lithium-ion battery technology. Oh, well, you will see also in the next slide, it goes roughly up to a bit less than maybe 400 watt-hours per kilogram. It's evolutionary improving by, I would say, by engineering victories primarily. The chemistry does not change too much today in the lithium-ion batteries. It's mostly engineering, I would say, that advances this. You see, and I will not speak here about power, I will come to that. And I think the elementary, I would say, calculus of battery is quite simple. So the energy you can store, of course, is the product of the charge you have in your electrodes times the voltage that you, so say, create between these electrodes. And the power you can get is then simply the resistance of your cell, the inner resistance, times the current density or current squared. We will see thermodynamics and energy density is pretty simple to be evaluated. If you have your materials, if you know your materials, and if you know the volume and the design of your cell, you can easily equate what theoretically is possible in storing energy. So energy is simple, but the kinetics is pretty difficult to be estimated. So that's something, that's why I think kinetics really demands for experimental studies. Now, the red and the yellow area, let me briefly explain. From the bottom part, I would say, I'd say from the poor part of this graph, the sodium-ion battery is coming closer. So that's for reasons of resources and primarily for techno-economic reasons. The battery world is developing sodium-ion batteries as an alternative at the lower end of the lithium-ion battery. At the upper end, there is the hope that solid-state batteries make it, and we will see what is this, why there is hope. But one point on the kinetics, I said estimating the thermodynamic, the energy content of a battery is pretty simple if you know your cell reaction, if you know what is in your cell. But kinetics is difficult because there's different levels, of course, of description. You first of all have to understand transport on the, I would say, molecular materials level. How is lithium and the electrons being transported? Then you make electrode out of that. These electrodes have may enter or may lead to curved parts for ions and electrons. You have tortuosity effects. You have pores here. Really a microstructure that complicates the kinetics, the paths of ions and electrons. Then, of course, you bring that in also to a cell. And so describing kinetics is quite, I would say, theoretically much more challenging than describing the energy density. Okay, and this is a graph at the end, I would say, of the quick introduction into batteries in general, which I really like to show. This is from Hong Li, a Chinese colleague in Beijing from the Chinese Academy of Science, and he put quite some data together. He published a paper where they went really to enormous values for a cell. So you see here 700 watt-hours per kilogram. This is really quite high value, where this red limit here is what in principle is possible for a classical lithium-ion battery with a graphite negative electrode and a typical oxide cathode. So this is what all has been demonstrated, but you see beyond that red limit, there is work also by Jeff Dahn from Canada, from Halifax, and you see all these cells contain lithium metal at the negative side, which of course has a higher specific capacity, charge per mass. More lithium is stored per volume and per mass in lithium than in graphite, of course. So you need to employ the lithium metal electrode. I know Hong Li quite well, and I asked him, okay, these values here, these very high values for these cells, this is, by the way, a liquid cell with a liquid electrolyte. These cells don't cycle really. So these are designed for demonstrating high energy density and high specific energy, but there is no true kinetic data in this paper. So I would say there's a compromise, and here it's optimized for energy density, but not for cycling. So if you were to design it better for cycling, you lose always specific energy. So that's, I think, the drawback of that. But in principle, you can come to higher specific energies employing lithium metal. But my belief is that in the liquid electrolyte, it will be very difficult to really employ safely a high-rate lithium metal anode simply due to the dendrite risk. Always metal deposition in liquid electrolyte will lead to morphological instability, so you get the dendrite risk. And I think many people, of course, think that this can only be overcome by having really I would say, a solid wall in the battery that avoids the dendrite risk. So the cells have to be partially solidified. Okay, and that brings me then to solid state batteries. And with the solid state batteries, I think I will concentrate on one type. I will have a short comment on the different types of electrolytes. And there, because both Linda and me, we enjoy work on inorganic sulfides type electrolytes for one reason, because these are the electrolytes so far that have the highest conductivity, in principle, in the solid state. So let's look a bit into that. And this graph is something which we felt motivated by semiconductor physics, where often semiconductors are being analyzed by plotting charge carrier density. So this is here then the lithium ion density, number density of ions per cube centimeters, versus lithium mobility. So the mobility of the ions, the electrical mobility, as you would also look for the electron hole mobility in a semiconductor. The product of the particle density, so the concentration times the mobility times elementary charge, gives you the electrical, or in this case, the ionic conductivity of the material. So these green dotted lines are isoconductivity lines. Now, to make that story short, in order to really have enough conductivity in your electrolyte to enable high power cells and to be competitive with liquid electrolytes, you have to achieve this 10 millisiemens per centimeter line. It's a bit betraying with the liquid electrolytes because this is the total conductivity of liquid electrolytes, where the cations only transport, let's say, 30 to 40% of the charge, because the anions are relatively more mobile than the cations in most liquid electrolytes. So this is, in the case of all the inorganic solid electrolytes, this is really pure cationic conductivity. And you see here are the sulfides. They can climb up quite high here. So this is the 10 millisiemens per centimeter line, which I think has to be met. Otherwise, you will not be able to have thick electrodes. If you go to lower conductivities, you will have too high overvoltages simply in your electrodes, and you will not be competitive with a good lithium-ion battery. So let's, for the moment, have the ambition really to meet and to beat liquid-based cells. Then we have to go here. And you see polymers, true polymer electrolytes so far, don't meet this limit here. So they have a mobility issue. What is important is, anyhow, all the liquid and organic and all these liquid electrolytes also are organic electrolytes. They have one advantage. They have a rather low concentration of charge carriers. In order to achieve the high conductivity of the inorganic materials, you have to go to relatively high charge carrier densities. So that's why we made this a cost axis in the case of liquid of lithium electrolytes. Well, if lithium cost doesn't matter, well, then it doesn't hurt. In the case of sodium, which I will not discuss today, of course, this is not a cost axis because sodium ions are cheap. So this is, I think, the picture is not so different for sodium electrochemistry, but for lithium, it's the way. Now, inorganic chemists like Linda are really very clever, and over the years really brought up the conductivity. So there are some lithium electrolytes that even have conductivities today of up to 40 millisiemens per centimeter, a factor of 10 more than liquid electrolytes. And there's even oxyhalides coming up or have come up originating from Panasonic, but there's meanwhile quite some work, and Linda is also very, I would say, there's lots of work from Linda's group, excellent work comes up to bring up these oxychlorides. You see, they have much lower lithium ion concentration and the mobility already is climbing up. And with the polymer sector, I would say there's not so much, I would say, improvement over the last years. You can, of course, increase the conductivity if you gellify them, if you add liquid electrolyte into the polymer. But that's not, I would say, a true polymer electrolyte. Okay, at the end, there is, I would say, in principle currently, and that's, I think, also how industry considers that, there's two options. Either you stick to liquid electrolytes or gellify liquid electrolytes, then you have gel polymer type electrolytes. That's what many Chinese companies do. They go for gel polymer type batteries, or you go for the sulfide type batteries for inorganic based batteries of sulfide type, maybe later, or a certain point, on oxychlorides, if cost effective and I would say pricey, not so expensive oxychlorides can be made that also are stable. Okay, and with that, we can enter into cell concepts, and let's just consider one cell concept, and that is what Samsung advanced a few years ago, and that is the so-called, they coined it as anode-free cell concept. Now, this is, of course, if you ever had a base course in electrochemistry, quite a bad term. There is no electrochemical cell without an anode. There is always an anode. So what they meant, of course, is reservoir-free. So I prefer reservoir-free cell. So you just have a current collector. You have your cathode, your positive electrode that contains all the lithium or sodium in case of sodium systems. And then you have an electrolyte. Either you have a liquid electrolyte or gel polymer, you have a true polymer electrolyte, or you may go to a true ceramic cell or to hybrid systems where you have a separator that is made of a different electrolyte than the catholyte. And these two cell concepts, I think, are something Linda and me are pursuing and many people in the world are trying to get, because if you don't bring lithium into the cell from the very beginning, of course, you save money. It's also easier to process because processing 10 micron thin or 20 micron thin lithium foils is pretty difficult, in fact, and not cheap. So it's much easier to I would say, whether it really works is another question, but I think it's a great idea, of course, to have all the lithium here and in the first charging step, just to place lithium here and to cycle it. Of course, what you need in order to have a good cell is 100% Coulombic efficiency. You should not lose any lithium. And this brings me, of course, to the first point. This is a bit different cartoon of such a reservoir-free cell. We have a separator electrolyte that should be rather thin. I would say 10 micron. Modern separators in your smartphones are even sometimes thinner than 10 micron. You need a thick cathode. Thick because you have to store there lots of lithium. You need a high areal capacity in order to get a high energy density of your cell. And then here the lithium is being cycled. And there's quite some issues all related with the different interfaces in these cells. And what my group is doing is try to understand really the microstructure and its correlation with the interfaces to bring down stack pressure. Because well, if you ever experienced mixing dry peas and beans, you will know there is always empty space in between, and contact may depend. In fact, if the peas and beans are deformable, will depend on pressure, and that is a key issue with solid state batteries. That so far they mostly operate at relatively high stack pressure, and that has to be reduced. Is one of the major issues. Okay, so let's look first for the as I said, looking into interfaces. Let's look to the negative electrode interface, and let's believe we can operate with lithium metal, and see whether the electrolytes are stable. And this is an important subject that, in fact, in any kind of solid state battery, the same cartoon could be principle designed for liquid-based cell. The negative electrode has a very high chemical potential of lithium. If you work with lithium metal, it is the highest chemical potential of lithium you can take. the standard potential of lithium. It's a high chemical potential. So this is chemical potential, not electric potential at the ends of your cell. The electric potential would exactly be the other way around. So there is a negative sign between the chemical potential and the electric potential. So let's think in chemical potential term. The cathode has a very low chemical potential, and the high chemical potential here can reduce your solid electrolyte. If it reduces the solid electrolyte, because the reduction potential that is, let's say, of the solid electrolyte is not high enough, then will use, and you will get an SEI. You will get a layer of degraded electrolyte. Now, think in terms of an anode-free or reservoir-free cell. This is, of course, bad. You deposit your lithium, and it will be consumed by the electrolyte. The question is, to what extent? Is it a minor process? Is it a major process? Because that determines whether you have to add a bit more lithium into your cell, and you have to make it bigger than necessary. And the cathode side, of course, the same happens. Maybe one more comment. This is something we just recently submitted. That is the self-discharge of solid-state batteries. I didn't know much about the self-discharge of lithium-ion batteries. So if you ask yourself, your lithium-ion batteries, how fast do they self-discharge? You have any idea? Or you will probably not realize, because with your smartphone you probably almost every day recharge it. But for EVs, there's a limit. The OEMs define that is a lithium-ion battery should not discharge more than 2% per month. In fact, they are better. Though often they are better than 0.1% per month self-discharge. So quite good even for long-term storage. For lithium-ion batteries, the self-discharge is very difficult to be equated, or let's say to estimate, because it's due to complex redox shuttles in the liquid electrolyte. Lots of stuff can move between the electrodes across the liquid electrolyte. In a solid-state battery with the inorganic solid electrolytes, only electrons can, so say, have an internal short circuit. So the question is, what is the minor electronic conductivity of solid electrolyte? And that is not well treated and not so well known, I would say. And we consider the self-discharge of solid-state batteries may even be an advantage, because if you really bring down the electronic conductivity to very low values, it can be that solid-state batteries hold their charge longer than a typical lithium-ion battery. Okay, now we wanted to know, in fact, how much lithium is being taken up by solid electrolytes, and Burak, a postdoc in my group, had really a very, I would say, as it's not my idea, I can say that I found it an ingenious idea. So he said, okay, I have a lithium anode here. This is my source of lithium, and here's my current collector, and I play the game of a reservoir-free cell. So I played lithium here. If my electrolyte is stable, the lithium will stay and stay and stay and will not react away. If my electrolyte reacts, there will form an SEI. It will consume by time the lithium until the lithium is gone. So I played, so this is cell voltage, this is time. I played here lithium, then I let relax, and then I wait. And as here's lithium, here is lithium, the cell voltage is 0 volt. If all lithium is being consumed and no lithium is here, the voltage will fade, and quickly. That has reasons, and it will get a rather high positive value. And you then simply measure the time here for the consumption. You make that in several steps. Each step looks the same. Nucleation, plating, consumption, and you see that gets longer and longer and longer. And what in principle happens is that you form this layer, and the lithium in principle takes, or the growth takes longer and longer, because it's a diffusion control process. And in fact, these curves for charge being consumed by the SEI over time are simple, mostly simple parabolic time behavior, as would say defined by simple diffusion across the SEI. And you see here a different solid electrolytes. This is a famous oxide, is the lithium lanthanum zirconate. And this graph, well, it rarely consumes any lithium because it's simply stable. There is one, there's the lithium germanium thiophosphate. It contains germanium. Germanium is easily reduced by lithium, and it consumes lots of lithium, even within, let's say, 150 hours. The agirodite, which is a lithium PS5 chloride, it's a sulfide electrolyte, Well, it's not so bad. It consumes, let's say, within 400 hours, 25 microamp hours per square centimeter, roughly. That's not so much, but it continues. So this is an issue. So there is an SEI forming, and this SEI is still today, I would say, not 100% understood. And what I can say is, anyhow, this can be designed. You can, of course, modify your solid electrolytes such that they form, let's say, less and more stable SEI, and that's a very important part, I would say, of the long-term stability at the end of any solid electrolyte with your lithium electrode. And you see here, effect of temperature. Of course, with increasing temperature, it gets worse. Something that is very important and surprised me is, now we had the garnet oxide as a stable electrolyte. So we used that, but nevertheless, we saw that lithium also disappeared. Where does it go? It goes into the current collector. So the current collectors, the metals, take up lithium. And copper, that is considered not to alloy with lithium, takes up quite some lithium. This is not so well known, but it takes up lithium. And meanwhile, I would say we have more studies of that. So copper is really taking up lithium. Of course, aluminum takes up a lot of lithium. In principle, stainless steel and nickel could be better current collectors. But on the other hand, in industry, nobody will quit copper because copper foils are a ready-made mass-marketed metal product. So I think that we rather have to see, is this really an issue or can that be overcome? Okay, and that brings me to summarize the stability issues. Let's look to the left side. So the oxides, in fact, we found only, I would say, the garnet oxide really is stable. That's why companies worldwide explore this material as a separator material. Problem is to make thin, 10 micron thin, large scale area separators, ceramic separators, cheap and pinhole free over square meters. This is a pretty tough subject. QuantumScape in the US, I think, is trying that since years. And you can see, I will say, you probably can see the shares of QuantumScape, whether they will be successful or not with that enterprise. The halides or oxyhalides are mostly unstable versus lithium because the metal ions are being reduced. I had a discussion with Linda on that point here, and we probably have to look a bit deeper into some of these materials, but this is most of these materials are probably not stable at the negative side. The sulfide and thiophosphates are all thermodynamically unstable, but they may form nice, stable, kinetically stable SEIs. Not all, so this is case by case. And polymers, I would say, well, it depends on the polymer, whether they are really stable. I would say if they are stable, then they're probably kinetically stable. They form an SEI, but this is definitely not my piece of cake. They also have an issue, of course, with may have issues with dendrite formation if you go to high rates. Let's exclude polymers here. This is, I would say, a bit beyond my expertise. On the cathode side, I will not comment so much on that. The halides may have a major advantage because particularly the chlorides may be stable at the high potentials of the cathode, whereas all the sulfides are not stable because the sulfur is easily being oxidized already at 2.5 volt versus lithium, so they need to be protected. So that means the best electrolytes we have with respect to conductivity are the worst when it comes to stability. And this is, of course, something we have really to take care. That's why I said design of interfaces. We have to design interfaces such that they survive. One comment is that if you have then a stable electrolyte and a stable separator, and you plate lithium, then the belief that they are dendrite that they're stable against dendrite is, of course, also, I would say, a misbelief. You see here a sulfide separator, a gyrodite separator. The lithium metal easily here went into the separator. There was lithium metal plating, well, and maybe a nucleus then cracked the separator here at the top, and then simply grew into the solid electrolyte. So still today, I think dendrite growth, even with solid electrolytes, is being considered as an issue. Not only because you have a stone as a separator, it will be stable towards lithium growth, because all these materials, of course, are polycrystalline. They have grain boundaries that may have different transport properties, may have different electronic properties, and it's a very complicated story that enters into that. So that's why Region had the idea to somehow mitigate this cracking issue. And this is a little funny story. He also looked for the influence of crystallinity. And again, I would say this is shaky ground for me. I'm a chemist and not a mechanical engineer, but there's lots of mechanics in that, exciting mechanics. In order to understand these things better, I think I should probably study deeper into mechanical engineering. But there is lots of, I would say, mechanical effects that are very important to be studied. And so I'm very happy that we can also cooperate with Jeff Sakamoto in Santa Barbara, Linda and me. We have a quite trilateral, I would say, little network where Jeff, as a somebody who's more trained as a material scientist in mechanics, helps us in understanding these issues. But what Jürgen did as an idea, he said, well, let's go simply to fiber reinforced separators, because in other cases, fibers can strengthen materials. So what he did was simply adding alumina fibers into this agarudite separator. And in fact, in these kind of dendrite tests, he could in fact extend the lifetime of separator to higher critical current densities, because these fibers simply, well, even if a crack initiated, the crack didn't grow so fast as it would grow in a simple separator. And as I see Mike Pope here, he has just this week had a workshop running on 2D materials. I just had, when I put the slides together, I thought maybe 2D materials could be something that help strengthening the separators and I would say improving the chemomechanics of a separator. So that's maybe something worth being discussed. Okay. I need to move on to the cathode side. So let's summarize briefly the anode side. Going for lithium metal, I would say it's by far not, I would say, solved to have a high rate, stable lithium metal anode. If you see that companies have solved that, I would say, okay, let's see the results. Show me real detailed results for current density, stack pressure, and anything. So I think there's still some way to go. And that's why, of course, often the announcements for solid state batteries are shifted and shifted and shifted. They will come, I'm pretty sure, but there is still issues to be overcome. I will be the first to congratulate if that works, but I would say I'm positively critical. Okay, let's go to the cathode side, where, of course, also contact is quite some issue. You know, these cathode particles and these cathode materials breathe if you charge and discharge, and they change volume. Radius isn't changing too much, maybe 100 nanometer or something, but it's enough to open up a crack to a solid electrolyte. And that can so far only be solved by, of course, having strong stack pressure. And often cells are being cycled at 100 megapascal. No way. No car would have enough, I would say, you would need quite some steel around your battery to keep 100 megapascal during operation in a car, and that is, of course, compromising the advantages of your cells. This is a cell we realized we have a big cluster for solid state batteries in Germany, which I'm coordinating. And this is how, in principle, you see again a cartoon where there's lithium, there's the separator, there's the cathode composite. And what we achieved was something where we went already into, let's say, 10 micron. So in principle, I would say we went to 20 and tried to come to that. So we are almost there. Lithium was brought into the cell. It was not fully reservoir free with 30 micron lithium, current collectors, and a rather thick cathode. And then you can achieve 465 watt hours per kilogram on materials level. There's no housing around that yet. That's not calculated. So with the housing, we may still be a bit below 400 watt hours per kilogram. But you see how difficult it is to really climb up. You have to fight by proper engineering at any corner of your cell to get really values that can surpass a lithium-ion battery. So working on solid-state batteries, every day I think, okay, really engineers did so well with liquid-based batteries to achieve the numbers we achieve today. Now, if you think, and of course there are still some issues to be solved, particularly rate capability and stack pressure, I think, and stability of this composite over time. Now, let's think of kinetics. I just learned that power tools, in principle, if you would like to buy a top chainsaw, and I think Canada, there's quite some chainsaws, I think here in the forests, often they like to see 10C. 10C means that you like to charge or discharge your battery in 6 minutes. So 10C means simply that you can charge or discharge your battery 10 times in an hour. So 6 minutes, full charge, full discharge. Of course, OEMs would like to see that also for cars, but it's not yet achieved due to all, I would say, instabilities in cells. But 10C would mean for this cell, 65 milliamps per square centimeter current density, which nobody ever, I would say, really tested. I think for lithium metal, I think Peter Bruce demonstrated 9 milliamp per square centimeter critical current density without cracking. So there's still some way to go to achieve that. So, but we already enter, I would say, when I think, and Peter Bruce went beyond 1C, which is already, I think, quite some success. So one issue then with the cathode, first of all, let's now slowly come to the cathode side is, I assume that a typical solid-state battery later may be a bilayer cell, where we have to use one electrolyte that cooperates well with the anode, stay with the anode, and one that is optimized for the cathode. That's a major advantage for solid-state batteries. In a liquid cell, you can't use two electrolytes. It's a liquid. It will mix. So the inherent advantage of a solid-state concept is that you can use two different electrolytes. But that brings up one new interface. We call it heteroelectrolyte interface, an interface between two different solid electrolytes. And the question is that good or bad? How much energy do I need to transfer an ion from one solid electrolyte to another electrolyte? There's not so much data about that. Meanwhile, there is more data, and particularly again from the cooperation between Linda, Jeff, and me, there's more. And this is a very nice cooperation between Wipin and Leo in my lab. So Wipin here in Linda's group and Leo in my group. They check different cell concepts where one is as a benchmark, really a cell concept where only a sulfide electrolyte is being used, cathode, separator, no new interface, just one electrolyte. Then a catholyte that is typically a halide electrolyte that has more stability towards the cathode material. And again, a sulfide electrolyte that has a nice SEI. And it is known empirically that, in fact, this cell concept doesn't work properly. You have to bring in a pure interlayer of the halide material at the end, so a kind of tri-layer cell, to really get it stable. And so they had quite some systematic work on that. And at the end, by systematic studies, they found out indeed that this is the benchmark cell, and what you see as capacity retention. So take this simply, these bars here, simply as measure of stability of these cells. So this is for this cell concept, rather stable. And these here, the dark colors, always are for the different materials. The higher bars, the more stable ones, are always this cell concept where one interlayer more is shown here, and where we avoid, in principle, triple phase boundaries between two different electrolytes and the cathode material. So clearly, this triple phase boundary has to be avoided. And going deeper into that, which I will not do, there is lots of chemistry going on at these triple phase boundaries. So the two electrolytes via the cathode material react, and that is the reason why this cell concept, this simple cell concept, which looks so nice, does in this case not operate so well, and we always need some more interlay, and then in principle you can achieve a higher stability. And then let's look really into the cathode, and I look a bit to the time. I think we start a bit late. Yeah, okay. So and let's look now to the cathode side. So first interface was the anode side. Second interface was this heteroelectrolyte interface, where the story, I think, is still not over, because the problem is, again, if you take two pieces of, let's say, paper on the micro scale, you will not have full contact. And contacting two solids to inorganic solids creates a lot of pores at the interface that causes constriction, only few contact paths, and the resistance always still is too high. And these interfaces have also to be designed, which I think is not yet done. Okay, let's, however, look to, I would say, somehow maybe the other most important part of the battery, and that is, of course, the positive electrode. It contains in the reservoir free cell all the lithium. So that's, of course, why it's so important to understand that better. Now, quite some time ago, Anja Bielefeld in my group, who meanwhile has her own group in Giessen, studied, in fact, what do we have to do to get a good cathode composite? And if I speak of composite, I mean the cathode material that stores the lithium and the electrolyte. Two different powders we have to mix. Think of two powders with particle size distribution that we have to mix. And I will show on one of the next slides that one of the best things we did was starting a cooperation with particle engineers. They know exactly how to mix properly. And as a chemist, I only learned how to mix liquids, but not how to mix solids properly. That's much more difficult, in fact. So what Philip did, he determined, in fact, what is really the conductivity, the ionic conductivity and the electronic conductivity. Both is needed in a composite because the electrons from the electrode and the ions from the electrolyte have to come together to store lithium or to get lithium out. So you need two, let's say, good path, interconnected path, ionic and electronic, to get a good electrode. Well, like in your lung, where you have, of course, highly tortuous ways for air and for blood in order to have an effective breathing process. So this is the same with ions and electrons in the cell. And here is, as a fraction of cathode material, Philip measured the electronic conductivity and the ionic conductivity. And of course, I would say quite trivial, if you have pure electrolyte, the ionic conductivity is high, pure cathode material, the electronic conductivity is high because these electrode materials are primarily electronically conducting. Ionic transport is there, but it's not so fast. That's why, of course, cathode particles are small, because in order to have short diffusion length for the incorporation and excorporation of the lithium. There's a sweet spot here somewhere, I would say, in the middle. And what Anja did, she calculated in principle what should be the conductivity of the electrolyte to have good path for the ions. And that is where the 10 millisiemens per centimeter came from simulation. We simulated that 10 millisiemens per centimeter are needed at least to have enough efficient ionic transport across that. Well, today, we and others did that, of course, a bit more professional by digitizing or making digital twins of real composite electrodes, and then by making, of course, digital analysis of the paths. And what we found out is that always in practice, so this is, in fact, the tortuosity factor, which is a measure of the difficulty of your path. The more tortuous your path is, the more curved it is. So the more difficult it is for your charge carriers to go through the electrode. So the higher, the worse. And those without a pattern here, this is for electrons, this is for ions, those bars without pattern are the measured values. And they are always higher than those being calculated from the microstructure. And the reason is there are features in the electrodes that are not, would say, taken by electron microscopy, nanopores, grain boundaries. So there is more defects in your practical electrode than you can get from microstructure analysis. So that's another reason why electrolytes have really to be excellent to overcome these microstructural issues. So in principle, they should be better than needed because you always lose effective conductivity due to microstructure. Okay, and that's showing how important pressure is. And I think not only how important pressure is, how depressing it is in a sense, because still today, you need quite some pressure to come to good charge, to get good charge out and into your cell. So with increasing pressure, decreasing pressure, in principle, the charge you can get out of an electrode really is changing quite a bit. So there is, I would say, already quite some success with less pressure sensitivity of your electrode. But I think this is still a key issue. And if you ask in principle, for example, EV producers that are honest, they would say, okay, of course, a solid state battery should have the same stack pressure as a liquid-based battery. And that is virtually atmospheric pressure, or maybe just 1 bar or something like that, 0.1 megapascal, but not 100. I made a comment here. I think what is really interesting is, and Linda is at the front end of that research, is there is materials, meanwhile, particularly oxyhalides, that are really viscoplastic. They can easily deform, and I would say there is again, for the interface design in cathodes, also clever materials design needed. Polymers may enter into that, but polymers have their disadvantages. At these high potential of cathodes, they are often easily oxidized and are not so stable. So that's why an inorganic solution might, again, be better at this point. There also, Linda really looks into that in depth. Finally, when it comes to the cathodes, I would say part of our work is to develop methods and to quantify things. And as one interesting aspect we found out by cooperating with the particle engineer. So Finn is a particle engineer, and Max is a material scientist in my group, and they cooperated on trying to better understand really the constraints of these composites. And there's a simple thing that is, I would say, trivial at the end, and that is what you typically do. You prepare your cathode, you measure it in a cell, then you get a certain, let's say, capacity out as a function of rate. And you think, okay, if this is not good, or my material is not good, or, well, I did not prepare my composite properly, whatever. But in practice, I think what is important to understand, there is two different effects that should be separated before you misinterpret your results. And one is simply by wrong mixing, you can have particles that are simply not connected. Let's assume that they are all connected to the solid electrolyte, the yellow background. But it may be that these four particles here, they are not electronically connected. No, they are isolated electronically. So that means they cannot be charged. You need to contact them fully ionic and electronic. And this has to be determined. This determines, so to say, I would say, static connectivity. And then if all are connected, then of course you can judge properly the kinetic effect, and that has to be separated. And this is one of the, I think, nice things. There was a study last year where 20 labs contributed, and this kind of benchmarking test showed that the 20 labs got all the same materials, had to construct the same cells, and there was a wide variation of results. And one of the major factors for that was that every lab, the students in every lab, mostly made their mixtures and cathodes mechanically with a mortar and pestle, and they mixed it a bit somehow, and then you have a human factor in that. And if you change that and go to a more, I would say, professional machine-made composite, immediately things get better. And then the data for the different, let's say, cathodes, each dot here is one cell, essentially, at different C rates. So, so this is 1C, 0.3C, 0.1C. You see these data really scatter quite a bit, but when you order them with respect to the utilization, really, the fraction of cathode particles being connected, and normalize it to that, then all these data nicely, I would say, fall onto one line, onto one capacity value, and that is then, I would say, correct. Then you can really judge, okay, my cathode material has this capacity at a given rate, and you do not include into your judgment of the kinetics of your cell those particles that are not being connected. So that's a very important step. And this is in this graph here. So there's a theoretical active mass of your cathode material. And there is always some loss of material due to the fact that not everything is properly connected. Let's call that static loss of capacity. If you account for that, then there is a remaining loss, and that's the kinetic loss. Only that is the kinetic loss. If you don't do that, if you don't account for that, you will think you have a much bigger kinetic loss to your system, because you would then simply add both together, but you have to separate these, and then you have a much better, I would say, judgment onto the quality and mixing of your cathode. We had not only measuring as a part of that cooperation thing, they both came up with a nice idea of a kind of chemical mechanofusion process for cathode building blocks. So what they do is now they mix cathode material in a dry process with a solid electrolyte, which is a halide electrolyte, and they create a little shell of electrolyte with a bit of carbon that then is able to deliver electrons as a kind of shell around the cathode particle. And these are then is a powder that is a building block for nice cathodes that operates quite well. So this is fully scalable. This is a mixing process. We would not have done that without cooperation with engineers, I think, on particles. Yeah, and two examples for the performance of solid-state batteries, just so that you see a bit of performance. So this is from a recent paper from the Bella Lab in Karlsruhe, which I'm directing. You see, this is a cell with a nickel cobalt manganese cathode material, classical sulfide type cell with an LTO anode, which is a lithium titanate, which is, I think, not leading to high energy density, but leads to relatively stable, say, data. But you see, after 300 cycles, still there's well, loss of up to, let's say, around 80% of capacity retention, which still is not good enough. No? With halides, that is data from Linda's lab here, where we contribute with some analytical data. You see also here 700 cycles for halide, which is a lithium indium scandium chloride. Quite impressive data for cycling. So these halides are, I would say, quite promising, and that's why Linda, of course, is pursuing the research into these halides. They may show more stability and maybe even more favorable mechanical properties. Okay, if you allow me 5 more minutes, I will end up with, I would say, some work which excites me most, and that is, again, going back to the beginning, that's a lithium metal electrode. The point is that lithium metal is, of course, so important because only with the lithium metal we can really climb up to ultimate, I would say, specific energies. But not so much is known about the lithium metal electrode, and particularly about the inner structure of lithium metal. You can imagine why. It's so reactive, it always has a passivation layer. So we wanted to understand more what is the microstructure of lithium metal. That goes back in principle to theoretical predictions by Don Siegel from Austin in Texas, who predicted that if you have small-grained lithium, let's even assume maybe nanocrystal lithium, diffusion in the grain boundaries is much faster. And so the idea was that these nanocrystalline lithium may have much better kinetic properties than large-grained lithium. We looked into that, and Dheeraj made some coarse-grained lithium and fine-grained lithium, where still the fine-grained lithium you see has quite big grains with 20 micron diameter. He was never able to make smaller-grained lithium because lithium is really growing fast. Its grain growth is extremely fast. But nevertheless, and well, these white lines, we thought may be grain boundaries, but the lithium has a passivation layer. It could also have been cracks in the passivation layer. So we were not sure whether we see really the microstructure. So that's an important point. Nevertheless, the small-grained lithium in stripping lithium delivered more charge than the large-grained lithium. So in principle, the assumption that small-grained lithium is better was okay. So the question is then, what is the microstructure of lithium in a reservoir-free cell? We don't use a foil, where the lithium is being plated. What is the microstructure of that? Nobody knew that. And this is work that two Tills in my group, so Till Fuchs and Till Ortmann did, the Tillies, essentially. And this is also a nice result of a cooperation. So this is a joint paper with Linda and Jeff Sakamoto. And what you see here is already, I think, a major result. So what they did, they created a workflow, a cryo workflow, fit cutting, and then ion polishing, and transfer everything under inert gas and cryo conditions. And what they then got is cross-sections of these electroplated, in this case, it's sodium on nasicon, it's lithium on garnet, and lithium on an agirodite electrolyte. And the color is simply indicative or indicating the orientation of a grain. So this is really electron backscatter diffraction, essentially electron crystallography, that only works if you have very clean surfaces. Clean surfaces, undamaged surfaces, then you get the pattern, the electron pattern, in principle, Kikuchi pattern one should get. And the shocking result was that these grains are really huge. You see here, 100 micron, they grew up to almost, in some cases, almost up to 100 micron grain size. So the idea to create small-grained lithium didn't work. And in fact, we never got small-grained lithium. In fact, this lithium that is being electroplated is so pure that nothing stops lithium from growing and growing to large grains. So you see, with making it thicker and thicker, the grains grow and grow. So we are still on the way to better understand what is going on together with colleagues in metallurgy. But meanwhile, we know that seems to be really even reversible. So grains grow with thickness, and if you then strip, the grains shrink again. It's really interesting from, I would say, crystallographic and metallurgical point of view. But then the question is, okay, is there any way to control the microstructure of lithium? The point is, pure lithium will not, I think you cannot control it, I think. It will always grow due to oswald ripening in principle, because the lithium is so fast. So we need to modify that. And this is what, in principle, Samsung already did when they in their paper on reservoir-free cells, because they used a silver carbon interlayer. I would call that electrometallurgy. So they put a dopant, in principle, at the interface, and if you then plate lithium, or if you do that with sodium, you can do the same. What you do then is, with a dopant with this interlayer, you go into a binary phase diagram and you create an alloy. And alloys typically have much less mobility for its constituents. And so what you see is the copper current collector is, of course, quite small grain, and the grains grew much, much bigger. So first of all, the current collector we found has no influence on the grain size. So the idea to use a current collector that is somehow, I would say, defining grain size of the lithium, that doesn't work. But if you then take, for example, gold as an interlayer, or silver as an interlayer, this is on titanium current collector, then in principle we see there is an effect. Grains remain smaller. I would say it's not super impressive, but you can somehow control the grain size already. So I would say this is a good starting point. Interlayers can control microstructure. In the case of gold, we even have I would say, a hypothesis, because what we saw is out from the gold interlayer, little lithium-15 gold-4 intermetallic phases, little particles grow, and we think that they really pin the grain boundaries and they can't move anymore. So there is, again, I would say this is electrometallurgy. You dope during plating and you get the dopant back if you strip the lithium, which is, I think, quite nice. The case of silver, it's completely dissolving in the lithium. There must be another effect which we don't yet understand. Okay, with that, let me come to the end. I think solid-state batteries really require both chemical and advanced mechanical microstructural design. There is room for design, and there is need for this design before they, I think, really operate properly. They will come. Don't ask me when. I think I'm not a prophet, but I think to get it as a mass marketed product will take some time. And at the end, there are two advantages, may not those advantages that were expected at the beginning. I think it really needs a strong collaboration between electrochemists and engineers. Inevitably, I realized that myself. The lithium metal electrode really has further to be improved, particularly the separator concept. I think at the end, a 10 micron thin separator has to operate stable against dendrite growth. And that's something that still has to be improved. And of course, cathode composites also need to be better designed to have stable, high-rate operation. So I thank the funding agencies, particularly BASF, for long-term funding, but of course also our federal ministry for lots of support, and other companies. I'd like to highlight that Linda is part of a big new cluster in Germany that works on post-lithium storage, where 3 universities cooperate. And with that, I thank you for your attention. And sorry for stressing time.
Excellent seminar. Thank you very much. I'm sure there will be questions. Show out.
Several quite related about copper.
The stability of
Copper.
yeah. This is an evening-filling subject. So if you look to phase diagrams, lithium copper, you'll find there's old phase diagrams that claim 20% solubility, 20 atom percent solubility of lithium in copper. Then there is suspicion, well, people suspect that this may only be due because in the old days, some of these phase diagrams are pretty old, that when they studied these phase diagrams, they studied maybe copper powder with lots of copper oxide on the surface, that this was not true lithium copper phase diagram. I think what is the best assumption we have today is that the lithium primarily goes into grain boundaries of the copper, that there is, I think, really a solid solution coming up. I know there's some papers coming up recently. I don't think that the bulk solubility of lithium copper is 20%. It's more, I would say, a grain boundary solubility. The diffusion is rather slow. So we estimated in the case of our current collector, which was a few, let's say 10 micron, we estimate that it will take a few years to saturate it with lithium. So it may be part of issues. But the most critical issue may be that the so-called bipolar cell concept, which that you have on the same current collector on one side an anode and one a cathode. And it was always assumed that if you use copper, that the two electrodes, of course, don't communicate. But if lithium can permeate, you have a problem with bipolar cell concept. So it's a, I would say, a relatively new open subject. There's not so many papers on that. Yeah.
Metal into effect, and how does it affect the whole?
Yeah, we looked at, so we just uploaded a paper into Chem Archive where we tested 3 different interlayers. One was silver, gold, and one was bismuth. Bismuth was interesting because if you take bismuth interlayer, you get just single crystal lithium, one big grain. So you promote grain growth. Silver and gold, I would say, avoid grain growth to a certain extent. If you look to the Samsung paper, they used silver and carbon. So the carbon also plays a role there. I would say we started all that work on studying the microstructure a year ago, and I can't give you an answer really what is the best on that.
Business with bismuth is interesting because it has the highest diffusion coefficient for lithium of all of those alloys.
Yeah.
By almost an order of magnitude.
Yeah,
and so perhaps that's what you mentioned, that there was low mobility. In fact, I think in the alloys there's high mobility.
Exactly.
And so that shouldn't really favor the little small grains. It should favor just what you see for business.
Yes.
But anyway, that's another subject for discussion. Mike.
A couple of questions. Thanks for a great talk, as always. So the gold on titanium, is that because you couldn't get adhesion on copper?
Yeah, I think, of course, adhesion, all that, of course, also goes into the, I would say, the consideration and the properties of these interlayers. Together with Jeff, we also have some work where already, if you just deposit, let's say, some nanoparticles of gold, so not a fully covering layer, just a few nanoparticles, which you could consider as seeds for alloy formation or anything, already improve the situation quite a bit. So I think the microstructure of the interlayer may be 2D or, well, virtually 2D, or particular will also have an influence on the microstructure, yes.
Second question is regarding it's like
The what?
think about a critical current,
Yeah.
a critical current density for these solid state batteries, right? I mean, traditional electrochemistry, you talk about like the diffusion layer, the boundary layer. In the solid state battery, there's no convection or anything. So the boundary layer is probably the actual thickness then of the actual solid state electrolyte, right? So then how could you ever get something like 50 milliamps per centimeter squared?
Well, this is it's a good question. So as I said at the beginning, thermodynamics can easily be calculated. So all the energetic properties of your cell can be well estimated, and we can estimate limits for that. Well, limits by thermodynamics. Kinetics have less, I would say, natural limitations. So if you ask what are limitations to kinetics by any kind of law, natural law, I would say there is not so many. If you can lower activation barriers and so on, you can achieve very high rates. So in fact, we investigated silver electrodes quite a while, long time ago, and we got ultra high current densities, exchange current densities that correspond, of course, then to very high critical current densities of amp per square centimeter. That worked. It is a question, I would say, of the quality and the microstructure of your electrodes. I can't yet tell you how it should look like, but I would not say, I would not assume that it's impossible to get 65 milliamp per square centimeter. But one has to demonstrate it and to find a way to get that, yeah.
Yeah, very insightful talk. In many places you mentioned we need engineering as well, and particularly for solid state batteries, good mechanical properties, for example. Would you be able to share your insights on what is good in this case?
Well, of course, what is good should be in that sense, because our cell is living in the sense there is always local strain coming up. No? So you lots of strain, in fact, at the metal side where you grow, let's say 20 micron and shrink. So there is lots of stuff going on. And the separator probably has to survive that. And the cathode side, you have locally growing and shrinking particles, and your local microstructure has to survive that. I think there has to be some mechanically adaptive, maybe interlayer. I would say always polymers would be ideal, or something that behaves like a polymer.
It's not just simple hard.
No, I would not say. No, I would say soft solid electrolytes already help in a sense that I'm pretty sure that solid state batteries as liquid-based batteries will have a formation cycle. So any liquid-based battery will, at the cell producer, being assembled, being charged for the first time. And then what happens is lots of gas is coming up because the SI forms and the battery blows up, then the gas is released, and then you can close it, and then you can sell your battery. It has had a formation cycle. In the case of solid state batteries, I assume that this formation cycle may be, in fact, a high pressure formation cycle where you form a proper initial pressure-induced microstructure that then has, under the, I would say, desired mechanical boundary condition, maybe just a bar, 2-bar sec pressure, has to operate. And I think as there is definitely chemomechanics going on, you need materials that are to a certain extent elastic, I would say, now, and stable. That's, I think, and chemically stable under extremely reducing and extremely oxidizing conditions. So this is quite challenging, but also attractive.
So when you're mixing and the ion conductor that you want, active material, your active material, right? That not applicable in this fast ion conductivity. Kind of like the
Okay. Yeah, I think analyzing what we did, of course, was I would say a simplification, assuming that the electrode material, so the storage phase, is indeed, I would say, exclusively an electron conductor, and all the ionic transport comes from the electrolyte. That, of course, is different for any cathode material. Cathode materials, of course, need to have ionic conductivity, but typically it's lower than the electronic conductivity. That's why for modeling often it is neglected. And it's in fact, partly, of course, also the electronic conductivity is a function of the state of charge. So if you really make proper modeling, you need, of course, also to take into account that the transport properties of the cathode material are state of charge dependent. Yeah. I was a bit oversimplifying at that point. Yeah, right. Exactly, yeah.
Bear with me and answer an engineering question.
Oh.
I was very interested to see the different active material utilization rates.
Yes.
In that collaborative study. Can you elaborate a little more on any trends? Obviously, using industrial equipment with higher quality powder and things like that, but for positing techniques and stuff that we can take back. But what was it?
Yeah, I think what is very important, first of all, is that I think what is important to get at the end, a good utilization is that you have that the solid electrolyte particle size distribution is adapted to the particle size distribution of your active material. Typically, these active material particles are on a few micron diameter size. Solid state particles typically are smaller, and they need to be smaller to, I would say, fill everything properly. That has, first of all, to be adapted. And then, well, the best is, in our case, we already saw a major improvement, not by making a hand mixing, but we call it an egg shaker. So it's a little, I would say, mill that has more reproducible mixing properties that the engineers in Braunschweig already simulated, so that we found most of the scattering already disappeared with a bit more professional mixing. So that was not 100 kilogram scale, it was really lab scale. So even on the lab scale, you can reduce scrap. And maybe one comment, which I'd really like to make, because if you see why at least in Europe, maybe North America is better, but I'm not sure. You see that the fact that Chinese cell producers are so successful is they started early and they managed to reduce the scrap of cell production to very low values. Definitely far below 10%, maybe even below 5% scrap rate. In Germany, there was a company, Northvolt, run by Sweden, and they failed after a short period of time. And one of the reasons was probably that they didn't manage to reduce scrap fast enough. So one has to accept that there is quite some learning curve to learn making stuff properly. And now going back to university and to lab, you can ask yourself, do you report experiments that don't work? Typically not. So we found in this benchmarking studies for coin cells that we sent out material to 20 labs. So essentially Nella did that from Bayreuth University. And she asked, of course, for the data of 3 cells, triplicate cells. Only 53% of all cells worked. So these 47% of cells that didn't work never show up in any typical paper. So we have no good culture to deal with scrap. And I think this is something we should, I would say, take more care, because later in industry, this is ultra important. So we should a bit more, would say, scrap attentive also in our research labs. Why does stuff not work so well? Not just throw it away. There may be important information in there.
This journal will be coming up soon. Things that didn't work.
The scrap journal. Huh?
Yeah, I was just wondering if you could elaborate. Did an experiment on mixing.
Yes.
Using high-speed mixer. Did you like manage to be able to fix a parameter, like how large your electrolyte and your? I feel like they're pretty big, very variable parameter.
Yeah. I think first of all, I think the problem is there is, of course, when it comes to solid electrolytes, only very few electrolytes, like the agurodite sulfide electrolyte, you can purchase from different producers, I would say, with different particle size distribution. And the particle size distribution is typically not something that is properly quantified if you buy it. So this is already a problem, I would say, in daily life in your lab. So you have to measure that yourself. So it's something that is so far, I would say, not too well at all, I would say, looked at. And I think we are scratching the tip of the iceberg currently at that point. And I'm not the engineer, so I would say I simply learned from the engineers that, and years ago, I think it was somebody from a cell producer who told me, give me a good cell chemistry, so give me the materials, and give me 4 years, then I make a good cell. So I can't give a proper answer to that. So I think we found that this mixing is critical, and you saw the utilization ratios were even approaching sometimes below 80% by improper mixing, of course. And that's something what, of course, I think the cell producers learn to do properly. If you ask ChatGPT, what is the biggest problem for, let's say, what is the major source for scrap in batteries? sheet production. So the electrode production, where you produce a slurry by mixing and homogenize it, a calendar. So this is the biggest source of any major, I would say, quality issue with batteries, and this will be the same in solid-state batteries, maybe even more critical. Yeah. But I'm not a specialist for that. I simply try to learn myself.
Critical density. So you often see this measurements being done in the trade.
Yeah.
Is this really a good descriptor?
No. No, I think, yeah, we did also recently a study with Deb Sakamoto on that, because often these critical current density measurements are done by having a symmetric cell where you just cycle a bit of lithium back and forth, but only small amounts. In a true battery, in principle, you, of course, you plate quite a bit of lithium, and you have to strip quite a bit of lithium, or maybe 20 micron maybe or something. So I would say proper critical or proper measurements to quantify, or let's say to quantify the quality of your electrode should look different. Should look for not the symmetric measurements, but really for unipolar experiments in order to get reliable numbers. Yeah. This is one of the, I would say, not so well covered subjects. There's improvement at the measurement side, I think, necessary. Yeah. Well, there was. Yeah. Mm-hmm.
Any changes in the ionic?
That's a good point. Yeah.
Do you think it would major effect?
That's really a very good question. So in fact, originally at that point, he started not with alumina fibers. He started with a nickel net, which is easier to have a net where you press your material around. But a metal, of course, in a solid electrolyte, that is an issue of later failure. So we had to get to something that is insulating. So we thought, let's take, well, the simplest we could get was alumina fibers. And then we stopped because he left for industry, and we will recontinue that because we think there must be more clever solutions. We found with the one-dimensional fibers no major, would say, impact on conductivity. And there's one important point is if the separator is thin, should be thin, right? To not lose volume. I think that is otherwise used for storage. If it's thin, the conductivity of the electrolyte, it does not need to be that high as in the cathode. So I would say the conductivity constraint, or let's say necessity for the separator, is only 0.1 millisiemens per centimeter. You can take worse electrolytes, and you can accept, I would say, loss of conductivity due to design, I would say, of mechanical reinforcement. I think at the end it counts. What is the resistance of the aerial resistance of the capacity of your separator? As long as that is acceptable, it's fine. Yeah.
Theoreticians or? No.
Well, I was not bashing polymer chemists. I was motivating them.
With that, let's thank Professor Janek again. And we will assemble with my lab group in the fourth floor boardroom, just an informal discussion with Professor Janek in 5 minutes. Good stuff. So,
it would be nice if you delete the.
Yeah, sure. Turn that off. I can't figure out how.
Nice.